Good morning, everyone. I'm Rosa Arboretti from University of Padova. And clearly, first of all, I wish to thank the scientific and organizing committees for all their work in organizing this conference. I'm going to introduce this session related to machine learning issues, and let me share the list of contribution. Just a moment. Yes, so here I am. We have 3 contributions, and the time allocated for each talk is 15 minutes for both the presentation and some minutes for questions. With questions at the end of each talk, please. And I will inform the speaker when about 3 minutes will be left, simply interrupting the talk, sorry for that, and saying 3 minutes left. So I think that we can start with the first talk related to machine learning models for the evaluation of students' career. And I invite Riccardo Ceccato to share with us the presentation.
Okay. Can you hear me?
Yes.
Okay. Can you see my screen?
Yes.
Is everything okay? Okay.
Yes, yes. Perfect.
First of all, thank you for letting me participate to this conference. I am Riccardo Ceccato, and I'm a PhD student from the University of Padova. And today I'm going to present the work machine learning models for the evaluation of students' careers that I carried out together with some colleagues of the University of Padova and Professor Cristina Tortora from San Jose State University. At first, I will provide you with some background information about the study we conducted in order to then introduce the analysis we performed and the results we were able to achieve. Finally, I will also briefly summarize these results and discuss about them. So, first of all, in 2013, the School of Engineering at the University of Padova decided to start a new project. They decided to create a new database for monitoring the students' careers. The idea was to start gathering data about students in order to then analyze them and to be able to improve teaching and use these insights also for the orientation of new students. For this reason, our team was asked to produce an annual report about the students' careers, containing information about the average grades, the number of the achieved university credits during the different sessions, about the attendance of the different courses, and so on. However, last year we were also asked to perform an additional task. We were asked to try to identify the most relevant features affecting some key students' performances during their academic career. In particular, we were asked to identify the discriminatory variables, allowing us to predict the probability of dropping out at the end of the first year, achieving at least 55 university credits during the first year, and finally the probability of graduating in 4 years. In this presentation, I will focus in particular on the first and the third problems, simply for the sake of time. I will show you how we took advantage of some particular machine learning models designed for classification problems in order to fulfill this objective. And in particular, we used these models in order to be able to achieve some accurate and reliable importance measures in order to identify the most relevant variables, allowing us to predict the probabilities of interest. At the same time, we use these machine learning models together with a particular tool, the partial dependence plots, allowing us to better understand the existing relationships between the features, the considered features, and the probabilities of interest. So we started from a pretty wide collection of data, about 3,084 students, containing several different information. For example, the background information, the demographic characteristics of the students, information about the admission process, and in particular about the results at the entry test, general information about the career of the students, and also information specific for each year and session. For example, the average grades and the number of achieved university credits in a specific session. Finally, we also add information about the graduation of the students, such as the year and the final grade. So starting from this data, we decided to apply some simple pre-processing steps. We dealt with eventual missing data, we removed some redundant variables, we removed also variables that could not be used for some specific analysis. That is, for example, when trying to predict the probability of dropping out at the end of the first years, we simply removed the variables related to the following academic years. And finally, we also tried to apply some data transformation in order to improve, essentially in order to improve the interpretability. During the modeling phase, we decided to apply several different machine learning methods, focusing in particular, so far, on support vector machines, random forest, and gradient boosting machines. Following the suggestion given to us by Professor Cristina Tortora, we decided to generate 100 datasets using the 70% of the observation in the training set. And on each one of these datasets, we applied all the considered models and tried to measure their performances on the portion of the dataset that was not used for the training. In particular, we measured the so-called adjusted rand index and used it to select the best model. This adjusted rand index was proposed by Hubert and Darby in 1985 and is particularly adopted for clustering problems. Indeed, it is based on the pairwise agreement between two partitions. However, Santos and Dembretz in 2009 proposed to adopt this metric also for classification problems. In order to compare the partition to evaluate the pairwise agreement between the partition determined by the predicted levels and the partition determined by the actual levels. These measures can vary between -1 and +1, with +1 that represents the perfect matching, the perfect performing machine learning models that we would like to achieve. So now, looking at the results of the analysis we conducted and focusing in particular on the prediction of the probability of dropping out at the end of the first year, we can see that we found out that the best performing model so far is a random forest, allowing us to achieve an average adjusted rand index slightly higher than 60%. This model appears indeed to perform quite well, as it could also be seen from the confusion matrix here reported that is based on the out-of-bag predictions. Indeed, we can see that we have a pretty high accuracy of about 91% and also high recall and precision. Now, focusing on the other hand on the importance of the different considered features, Okay, focusing on the importance of the different features, I found that the most important one is the average grade, immediately followed by the fulfillment of the additional learning requirements for mathematics during the first year, and several other variables related to the number of university credits and the average grades achieved during the different sessions. Trying to deepen the understanding of the relationships between each single feature and the probability of interest, we were able to find out some pretty interesting results. For example, you can see from the partial dependence plot that for the average grade, we have a pretty peculiar pattern. That is that Reasonably, we have that for students having a lower average grade, we tend to have a higher probability of dropping out at the end of the first year. But at the same time, this probability is quite high also for students having an average grade of about 30, and this is quite strange. We tried to explain this, and in our opinion, this is probably due to the fact that among the students achieving the highest grades, as you can see from the box plot here, there are also students that managed to achieve only a low number of university credits. And so what does this mean? It means that here we have also students that managed to pass a certain number of the easiest exams, but fails to pass the most difficult ones. And so although they succeeded in the easiest ones, they are discouraged by this and tend to leave. And also maybe students that managed to pass only 1 or 2 exams, and so they still need to take a lot of tests to complete all the university exams in the set time period. Now, focusing on different, some other variables that showed pretty interesting results, you can see that also the fulfillment of the additional learning requirements during the first year tend to lead to a lower probability of dropping out. And a similar conclusion can be taken looking at the entry grade. This particular variable, indeed, and the related partial dependence plot showed also the efficacy of the entry test in evaluating future students. Given that for students having an higher grade at the entry test, we tend to have a lower probability of dropping out. Now, focusing on the prediction of the probability of graduating in 4 years, again, we found that the best performing model was a random forest. Random forest granting us an average adjusted rand index slightly higher than 80%. Here, investigating the importance of the different futures, we found quite predictable results. Indeed, the most important futures essentially are the ones related to the achieved university credits and the average grades achieved during the different sessions during the different years. However, again, we appreciated the importance of fulfilling the additional learning requirements during the first year, and similar conclusions can be taken also looking at the results of the entry test. Here, looking at the partial dependence plot for the average grade, we can see that in this case, the variable has a positive effect on the probability of interest, with this probability that sharply increase, moving from an average grade of about 21 to an average grade of 25, while for the highest grades, more or less, we have the same probability of graduating in 4 years. So, thanks to this study, we were able to identify several different relevant futures, allowing us to predict the probability of dropping out at the end of the first year and the probability of graduating in 4 years. The most important variables, quite predictably, was the ones related to the number of university credits and the average grades. However, we appreciated also the importance of fulfilling the additional learning requirements during the first year, and also we appreciated the efficiency of the entry test in evaluating future students. Several other interesting results were achieved during thanks to this study, but for the sake of time, I omitted them, I would like only to stress out that commonly the least important variables are demographic variables and also the type of high school and high school graduation rate that we thought to be more important. However, this study is clearly still going on, given that we still need to better investigate the choice of the optimal machine learning model, again keeping also in mind that we would like to frequently update this analysis, the results of this analysis, and to expand it to different schools at the University of Padova, in order to provide our university with valuable and reliable tools for allowing them to improve teaching and to be used also for the orientation of new students. Here, if you want
to... Riccardo, 3 minutes left.
Okay. Here you can find a brief list of useful references that you can look at if you are interested in deepening the understanding of some of the concepts I introduced during my talk. And this is the end of my presentation, and I would like to thank you for your attention.
Very well.
Thank
you. And I think that we have time for some questions or comments. Are there any questions or comments? Any comments or questions? Oh. Okay, so I think that we can move on to the second talk related to machine learning algorithms and design of experiment for product innovation. And Luca Pegoraro will present the talk.
Yes. Good morning. Okay, I think that now you can see my screen.
Yes, perfect. Thank you.
And thank you for your introduction. I am a PhD student from University of Padova in management engineering, and today I'm talking about my work on machine learning algorithms and design of experiments for product innovation, which is a joint work with Rosa, Arboretti, Riccardo Ceccato, and Luigi Selmaso from University of Padova. So, very briefly, the outline of my talk is as follows. First, I will start by introducing the topic of statistics for product innovation. Then I will go on with the presentation of the literature background and statement of my study objective. Then in the second part of my talk, I will proceed with the presentation of an industrial application in the chemical industry, which function as motivation for my work. And finally, I will conclude and present some ideas for future work. So, when talking about statistics for product innovation, I like to use this quote from this paper of George Box and Patrick Liu. And in their work, the authors state that the innovation in the design and manufacture of processes and products usually comes about as a result of careful investigation, which is a directed process of sequential learning. So by using this kind of definition, a topic that naturally comes up is the one of industrial statistics, because through the use of industrial statistics, it is possible to enable the generation of knowledge about the phenomenon under investigation. And as you know, industrial statistics has been widely applied for product innovation since decades. So we can state that now the relationship between industrial statistics and product innovation is very strong, mainly because of the use of the scientific method which characterizes industrial statistics, and also because through the use of the tools of industrial statistics, it is possible to assess the causal relationships that govern a given industrial phenomenon. Another topic that can be introduced is the one of machine learning that is widely applied in the most disparate settings and also for product innovation. However, unfortunately, as of today, the links between machine learning and product innovation are rather weak. And since through the use of machine learning, it is not possible to enable the generation of knowledge, the investigation part, which is needed for robust product innovation. This is mainly imputable to two factors. So the first is the fact that the models of machine learning are very often of the black box kind. So it is difficult to explain the rationale which drives the algorithm. And then we also have the fact that in the typical implementation of machine learning, there is no information is provided about the uncertainty of prediction. So the idea of this work is to try and draw a tool coming from the toolbox of industrial statistics, which is design of experiments, and combine it and use it as a support for a subsequent phase of machine learning modeling in order to find out if by using this kind of combined approach, it is possible to achieve the robust conclusions which are needed for robust product innovation. So here in this slide, you can see the literature background. This is the result of a literature review, which has been conducted recently this year. And it was carried out using both Scopus and Web of Science. And we found out using three sets of keywords, coming the first from the field of design of experiments, the second from the field of machine learning, and the latter one from the field of product innovation. After some cleansing of the database and removing the duplicates, we came up with a total of 87 papers. And as you can see in the yearly distribution of the publications, we have quite of a spike in recent years, meaning that this seems to be a hot topic and a relevant topic in today's discussion in statistics. Below, you can see in the pie chart, you can see how these papers are organized with respect to the research methodology, which is applied and used in the publication. As you see, we have for the vast majority of cases, we have case study applications. Then in some over 70% of the times, then around 13% of the times we have studies of case studies which are supported by a conceptual part. Then we have some reviews at 7% of times, and also some other categories which are basically a mix of different research methodologies such as conceptual and simulation and case study, etc. In the right part of the slide, you see some preliminary descriptive, let's say, results of this review. The first result is that in the vast majority of cases, the machine learning algorithm of choice is the artificial neural network. As you can see, more than 90% of the times, the machine learning algorithm applied to design of experiments data is the artificial neural network. Then another result is that in this context, machine learning is applied to small data. Of course, this may be not surprising since we are talking about the context of industrial experimentation, meaning that it is very difficult or rather impossible to achieve the volume needed to enter the domain of big data. However, it is quite surprising, as you see in the box plot, that more than 50% of the data sets of the design of experiments data sets used for machine learning modeling contain less than 29 instances. Nevertheless, in the literature, we found out that still the application of machine learning models has some advantages in terms of predictive performance with respect to the quadratic regression with the interactions, which is the typical model for response surface methodology. The literature highlighted some gaps as well. The first of which is the fact that just very few papers focus on the implications of a joint adoption of design of experiments and machine learning. And this is a direct consequence of the fact that over 70% of the publications are mere case studies. Then we have the fact that the role of prediction uncertainty is underemphasized for machine learning applications on design of experiments data. As you see in the pie chart, for more than 90% of the cases in the articles, we only have point predictions without any kind of inclusion of confidence intervals or prediction intervals. And then a third gap concerns the lack of causal investigation when dealing with machine learning predictive algorithms. For 50% of the cases, the analyst do not even make a tentative to try to illuminate the black box and try to explain the role of the different variables in the algorithm. Then for about 20% of the times, we have the application of some tools coming from the field of response surface methodology. So, for example, interaction plots and contour plots, but applied on the polynomial model. And then for around another 20% of the times, the analyst tries to explain the role of the different variables in the algorithm using tools from the graphical kind, such as surface plot, to making sensitivity analysis or also interpreting for example, the weights in a neural network. So again, since the objective of the study is to generate knowledge to enable the investigation part, which is needed for robust decisions in product innovation, we have the need to address the limitations, the gaps that we have found in the literature. So for what concerns the quantification of uncertainty, it will be, we should choose appropriate algorithms and strategies. And then coming to the causal investigation problem, one first thing worth noting is that in this case, since we are applying machine learning models to experimental data, by default, we can achieve some level of inference, since we are not applying the algorithms which are driven by correlations, but still we are not applying them to the mere observational data, which is the typical application. Then another higher level of interpretation can be given by a quantification of the variable importance. So coming to the industrial application, in this case, the objective of the study was to develop a platform for prediction of new paint covering capacity based on the formula composition. And the first step of the study, which is of interest for us today, deals with the characterization of the relationships which exist between the formula composition and the covering capacity on different types of material. Below, I tried to convey and show the framework adopted. As you see, it is divided in two blocks, the first of which deals with the design of experiments, and the second is about the machine learning modeling. For the first block, the first step is the design generation. In this case, we opted for a box blanket design, mainly for the higher efficiency of this design. So we had 9 factors, which are the components of the formula on 3 levels of occurrence. And we obtained an optimized design with 70 runs. We added a replicate, so we came with the final numerosity of 140 runs. Then, in the second step, we carried out the experiments and we measured the response, which is the covering capacity on 2 types of material. And this covering capacity is measured by means of a reflectance spectrophotometer, which outputs a number from 0 to 100, where 100 indicates the perfect covering capacity. Then, in the step of machine learning modeling, this initial data set is split in training and test set. And the training set is used to train the algorithms with a 5-fold cross-validation strategy to tune the hyperparameters. And then the optimal algorithm is applied to the test set in order to carry out an evaluation of the model. Then, of course, the last step concerns with putting into production the algorithm, meaning to perform predictions on new ANSI formula compositions. So coming to the machine learning modeling step, we opted that the first algorithm that we tried was a random forest. And after some tuning, we came up with a forest with 2,000 trees. And in this case, the variable importance was assessed with the permutation approach, which is natively provided by the original implementation of random forest. Of more interest is the discussion about the uncertainty of predictions, which is estimated as the arithmetic average of the bias-corrected variance estimates obtained with the jackknife after bootstrap and infinitesimal jackknife approaches, as proposed by Wager, Hastie, and Ephron in 2014. And in the right part of the slide, I try to convey in an intuitive way how the jackknife after bootstrap approach works. So we have the original data from which several bootstrap samples are drawn, and to each one of these samples we have a tree which is grown, and so we have as many predictions potentially as we have trees. At this point, the jackknife is applied, meaning that the different trees are grouped according to which instance is missing from the training data. So for example, in the first two trees on the left, tree A and B, we see that we have the red instance which is missing. Then for B and C, we have the purple instance which is missing, and for C and D, we have the yellow instance which is missing. So as such, we can obtain several small random forests. Thus, we can get at the end of the procedure a mean prediction, but also an estimate of the variance of such prediction, which is the confidence interval of the final prediction. Another strategy, another algorithm that we tried comes from the family of artificial neural networks. In this case, we opted for an ensemble strategy since we wanted to reduce the variance of the prediction while not increasing the bias of such prediction. So as such, we opted for 100 base learners in each ensemble. And these base learners are networks, shallow networks with 1 hidden layers and up to 10 nodes. And in order, of course, to achieve this uncorrelation between the base learners, which is needed for reduction of the variance, we randomly initialized each weight and differently each weight of each network. And the variable importance is assessed by the calculation of the sum product of the input hidden and hidden output weights between the input and the output nodes, as proposed in the paper that you see in the reference. And then for the uncertainty of prediction, again, we leveraged the ensemble approach, since from each ensemble we can get 100 point predictions, and as such we can calculate the relevant percentiles and include them as an estimation of the variance of the prediction. So,
sorry, 3 minutes left.
Thank you. So coming to the results, as you see here, we have the results for what concerns the variable importance. And in the first case, in the figure A, the first response, we have the random forest, which proved to be superior. And in this, while in the second case, the artificial neural network ensemble is the model to go with. And as you see, we have a ranking of the importance of the variables, and this kind of information is crucial to provide to the subject matter experts, in the case the chemists, that can use this kind of information to support the empirical estimation and prediction made by the algorithm. Here you see the results in terms of predictive performance, and in both cases we have good performance of the algorithms, since we have in the first case a correlation between predicted and observed data which is above 96%, while in the second case we have a correlation about 88%. And as you see, we do not only have point predictions, but we also have an estimation of a confidence of such prediction. And of course, this can reinforce the conclusions of the study and of the algorithm. So, in conclusion, we have seen that in order to achieve robust results for product innovation, there's the need for causal investigation and a quantification of uncertainty. And this can be achieved also with machine learning models. And a valid approach for research and development is, as I said, made of 2 phases, one of design of experiments and the second of machine learning modeling, when data needs to be generated and not only captured. Then some ideas for future work. Of course, we would like to assess the performance of the algorithms or on new formulation or new data to test their robustness even when the conditions are slightly diverse. And then we want to use the predictions of the algorithms to rank new tentative formulations and also to find the best composition overall. So here I provide some references from the literature review, and I would like to thank you for your attention.
Thank you for your presentation, and I think that we can allow one question or comment. Any questions? Comments?
Hello, good morning, everyone. I'm Luigi Salmaso from the University of Padova. I wish to ask Luca if he can explain maybe which kind of design of experiment is could be considered for those predictions combined with the machine learning models.
Yes, thank you. So in the literature, we find that the most disparate kind of designs from the response surfaces, the box bank and the central composite design, and also a lot of Taguchi designs. But in my opinion, and as confirmed by some recent literature that I found from this year and the last year, the most interesting framework may be the one of active learning or adaptive learning. Which consists on an iterative procedure which starts with a small initial design of experiment, which can be, for example, of the space filling type in order to reduce the bias of the final algorithm, the final machine learning algorithm. Then on this first initial data set, we can train a first initial model, machine learning model, and then use an acquisition function. For example, comes to my mind the expected improvement function, which is a specific kind of function that tries to balance the exploration of the design space with the exploitation of the knowledge which is already available in the design space, in order to suggest further new combinations within and also outside, if possible, of the design space, in order to go close to the optimum of the function, to the optimal configuration of the design. And this procedure can take several steps. So we can have the initial design, then we train the algorithm, use the acquisition function, and we go to the lab to test the new formulations, the new design of experiments combination. We use this new data and we integrate the initial data set and we retrain the algorithm to achieve better performances. And maybe again, we try to apply this acquisition function in order in several steps to reach the optimal configuration. And at the end of the day, we may also save some runs, so some costs in terms of experiments in this way.
Okay, thank you.
Thank you.
Very well, thank you again. And now what follows is the last contribution related to topological methods for social data analysis, an overview, and Sara Scaramuccia will present this talk.
Yes, I'm here. I'm just trying to share my screen. I'm sorry because I have some problem with the system preferences. I try to.
Sara? Are you here with us?
I am back. Okay.
Okay, very well.
Can you see my screen?
Not yet.
You could not see anything.
Yes, yes, perfect. Thank you.
Do you see anything now?
Yes, we can see it.
Okay. So here are the slides. Perfect. I'm sorry for that. Okay. By the way, I'm Sara Scaramuccia. I'm a postdoc at Politecnico di Torino. And today I will talk about it's a kind of an overview. It's not a collection of results of our group, but it's simply that we would like to understand if our expertise in topological methods can have some expressive power in social data analysis, especially when we are interested in kind of data set representable with networks. And I will go through a brief introduction to topological data analysis, and then we will see two small applications we have in that field. So what I mean by a network is a graph, but we can think about a collection of entities. And in our example, one entity might be an author inside a network of collaborations. So an edge in between two authors represents a collaboration between the two. And we can think that we can possibly give weights to our arcs in our network according to the number of collaborations. So it's just an example of a data set we can represent this way. And once we have that, most of time in social domains, we are interested in understanding some maybe local information, like the relevance of one node inside our network. So in the example of authors, maybe the importance of that author inside a community. Or we might be interested in global information, a kind of we can think of a segmentation of the domain into communities of authors. And once we have that, we usually build up similarity functions based on distances among based on a lot of things, but for instance, there may be distances among global measures or distances among some domain-specific evaluations. And what we will see today is based on the idea of building similarity functions. And I can see some noise in my ears. If there is anybody with the microphone open, please. Thank you. And okay, we are focused on topological descriptors in order to build similarity measures in a network. And what we mean by topological descriptors. Okay, topology, it's a branch of mathematics and which studies basically, roughly speaking, characterizes shapes according to transformation, which are continuous. That is, they are not involving tearing apart part of our shapes or gluing together multiple pieces. But we are allowed to stretch our shape, to bend. So it's not something, it's something that alters the metric of our space. So in the picture, you can see that the rabbit, from the topological point of view, is the same as the sphere. And what topology cares sometimes is it's a very coarse qualitative description, like the number of holes. So topologically, I can say that the torus is different from the threefold torus and from the rabbit. And the example I gave you of the holes is not just to say, but it's precisely what homology, one of the main topological invariant, is retrieving. So we can say that homology is counting the number of connected components when it is considering degree 0. One cycles, and one cycles are the independent loops we have in our shape. So in the example you can see the torus, and we can say that there are two independent loops.
Sorry, Sara.
Yes.
Sara, sorry, but you are still on the first slide, probably.
I am changing the slide in my laptop, but you cannot see. Okay, thank you for telling me. I try to unshare the video and do it again. So we have missed a lot of slides. Now, what
okay, now it is okay. Thank you.
Okay, so we can start from here, which is a crucial point. So I was saying, what is a homology? We are counting the number of those independent loops. So in the torus we can count two, the parallel and the meridians, and but we can go higher in dimensions. So we can count the number of we call it K cycles, but they are voids, like the void within a sphere. And the main tool in topological data analysis is not precisely computing homology, but computing persistent homology. That is how homology changes, not on a single shape, but on a family of shapes, where those shapes are increasing. They are getting bigger and bigger. And what is very powerful in topological data analysis in general is that this construction is stable, is robust to noise, and sometimes when it's difficult to choose one value for one single parameter of our data set, we can consider the whole families of the whole range of values and study the persistence of homology to retrieve which are the most important values of our parameters, at least from the topological point of view. In our case, so when we are interested in networks, we can start with the networks, the weighted one. So like the example of the co-authorship network I gave previously, and we can build up a flag complex on that. What does it mean? We start with all the vertices, all the nodes at the beginning, and we make the parameter epsilon vary, and we take all the edges with weight lower than a fixed value epsilon for our parameter, and at that stage we add one K simplex for each K plus one click we have in our network, where a click is a subgraph which is complete, so every node is connected with all the other ones. Here you have an example. So we have our network. I fix my parameter at value 1, and I have only the red click, that is a 2 click. But if I increase the parameter, multiple clicks are entering my graph, and possibly I should add something with a higher dimension, like a tetrahedron. The orange one is a tetrahedron, and we can go higher in dimension. Here we can take these constructions and see how what it has been studied so far in the field. And the first application I want to show you is this one from Cartens et al. In 2013, where the purpose was basically to understand if there is some persistence information in exactly the network I was talking about, so the co-authorship network. If persistence can say something in that case, and they did this. They considered persistent homology, like I introduced it before, and compute the persistent homology signature, which is called the barcode. What is the barcode? It's a collection of bars, each one representing one homological feature, one k-dimensional loop. So the blue bars are the zero-dimensional loops, also known as connected components. So we have 4 at the beginning, and they are merging when I am changing the value of my parameter. And then we have also the red bar for the loop, which is born at step 2. We have a kind of signature like that once we compute persistent homology. And what authors found is that if they simply count the number of bars, the zero-dimensional ones and the one-dimensional ones, they were able to say that their network, that is the co-authorship networks, behaves in a very different way from a random one. So there is a kind of information to disclose, information which is topological to disclose in this kind of data set. Of course, it's the preliminary work. And in the end, they try to use the bottleneck distance, which is the standard distance in between persistent homology signatures, so in between barcodes. And they were able to find that all random networks were more similar than the co-authorship network with respect to the random one. So we can take out of this work the fact that there is some information to be disclosed in this kind of social networks. But of course, there are also some troubles, and the troubles are related to the interpretation we can give to those loops, zero-dimensional loops, one-dimensional loops. What is there is no straightforward interpretation, but we can according to the change of the domain, we can try to understand what is the interpretation to be done. So, for instance, in the co-authorship network, we see that the connected components are made by nodes that are not very strongly connected, but stronger connections are made in between different communities. Or one loops are collaborations between authors where a new collaborations happens between 2 new authors, but there are co-authors that previously worked together. This is very complicated to analyze, and this is why other authors have tried to adapt the persistent homology pipeline to measure something different, to measure the evolution not of loops but of k-cliques, because the concept of k-cliques, that is complete subgraphs, is more related to network analysis. And this is the last applications we see. There is this nice work from where authors analyze the Shakespearean plays, and each one can be represented by a network, a weighted network where nodes are characters, edges are in between characters if they are in the same scene, and they are weighted according to the number of interactions. And in that case, we can adapt the persistence pipeline in this way. We can, for each degree k, consider the dual graph, where each node is made by the k clicks in the original graph, and we have edges in between k clicks whenever the k clicks are adjacent, that is, whenever they share a common k-1 click. And if we analyze the persistent homology in degree 0, that is only the connected components, the persistence of the connected components in this dual graph, we can also define, we can also turn the barcode in something where something called the persistence indicator functions, that is counting functions of the k click we have alive at the fixed threshold, and by considering that, we can classify comedies from tragedies, from histories in this data set, and we can find something very interesting, because comedies, for instance, have many more interactions in lower dimension, that is in degree 0, in degree 1, and that might correspond to the presence of subplots, which are more present in comedies than in tragedies, and this is very interesting. So to sum up everything, I presented the persistent homology pipeline as the main tool in topological data analysis. We have seen the barcode, which is the outcome of the analysis, and how we can compare barcodes with the bottleneck distance, and two applications. And we have seen that there is some expressive power to be disclosed from persistent homology, and there is some intrinsic adaptability of this pipeline to multiple domains, and in the specific field of social domains, this is a very open field, because applications are still limited in data set size, and the meaning of loops and k clicks and so forth is very something to be studied, better studied. So I thank you for your attention. I leave some references if one is interested. Thank you.
Thank you, Sara. Any questions or comments? I have a short question, Sara, if I may.
Please.
Just if you can give us some ideas of possible future steps of your work, also related to social data, textual data, some ideas.
We were trying to see if we can kind of adapt those topics based on networks to kind of help recommendation systems, but it's a very big in this. I give you an example. Maybe you want to track the customer behaviors, and you want to build up a network where items are connected when there is some customer that buy them, and we are trying to investigate if topology is able to help in recommendations.
Very well. Thank you again, Sara. And I think that we can stop here. And I wish to thank all the participants and all the speakers for their contribution that show how new perspective and machine learning techniques, network techniques can really contribute in different fields, from social data to experimental data for product innovation. And thank you, Corrado, for the invitation. I leave you to go ahead with the conference.